So we can continue our discussion about the characterization of the membranes. So far we have talked about the history and the preparation of the membrane, but the membrane actually has some pores or free volumes at least, or small spaces for the transportation of transport of the penetrants. So then what about the size of your pore? How about the distribution of the pores in your membranes? Do you have the pore on the top of or surface of the membrane, or bottom of your surface, the part of your membranes, or even the throughout the membrane? So this is the question that we can raise, and from now on, I think we can talk about how we can characterize the membrane in terms of the physical aspect, as well as the transportation aspect. So we'll talk about the flux and the permeance, the permeability of water, or if you are using the salt solution, then we have to think about the pure water flux, but we have to think about the rejection of the solute as well. So from now on, I think we can talk about the characterization, and this characterization is very important in the membrane research and development in order to design some new membranes as well. Right? And also, the membranes are quite different in terms of the properties of the membrane, and also the application might be different, although we are using the same type of the polymer. Right? So we have to think about how we can characterize this membrane. And the characterization methods are related with the pores. So we have to characterize the porous characteristics or natures. Typically, the membrane could be dense, but membranes usually have some pores for the transport of the other things as well. So the characterization of the porous membranes are the following. For the microporous, microfiltration and ultrafiltration membranes, we have to think about the pure water permeability, or pore size distribution, molecular weight cutoff. Okay, for those of you who know about the molecular weight cutoff, I think it's okay, but for those who do not know about, you also know about the molecular weight, but what about the cutoff? Okay, so we will define what's the definition of this cutoff. Other characteristics are that we need to know about the nature of the membrane material, whether this polymer is hydrophilic or hydrophobic, or positive charge or ionic charge, and also the structure of the membrane. So this part has already been discussed in the membrane preparation method in detail, and about the mechanical properties and thermal stability and chemical stability. So we will talk about how we can characterize those properties and transfer properties. First of all, the pure water permeability, so-called the PWP, is the first thing that you have to think about when you're dealing with the water separation. Okay? Whether you're working on the microfiltration or ultrafiltration, you have to think about the PWP anyway. So you have to first think about the flux J through the porous medium. J is equal to the difference between the applied pressure and the pressure that you get in the permeate. So this is the pressure differential between the feed and the permeate, and eta is the viscosity. Eta is the viscosity of the solution that you're dealing with. So if you have a highly viscous solution, then the flux is reversibly dependent upon the viscosity of the solution. If you apply the high pressure in the feed, then delta P is larger, so that it is dependent on it is related with linearly with the flux of your solution. What about LP? What's the LP? So LP is the solvent permeability, and so we have to think about this LP anyway. So if the permeability is the same, permeability is related with the structure of your polymer, structure of your membrane. If your membrane has a highly porous in nature, then LP might be higher. If you're dealing with a dense membrane, then LP might be quite low. Okay? So this might be a constant for the flux. So flux depends upon the linearity of the linearly with the permeability, but this flux depended upon the pressure and the viscosity. Usually, the pure water flux, flux is of the microfiltration membrane is ranging from several hundred liter per square meter per hour per bar to the several tens of thousands of liter per meter square per hour per bar of the flux. So the flux depended upon pressure, and so on. But this L is independent of the pressure. So L is independent to the pressure, whereas the flux depended upon the pressure that you apply. So this is LP is the parameter which is intrinsic property of the membrane itself, whereas the flux is not. Flux depended upon the membrane and the pressure and the solution that you are dealing with. So you have three different parameters that you have to think about. So bear in mind that the permeability and flux are quite different. Okay, permeability is the intrinsic property of the membrane. Intrinsic property of the membrane. It's not changing. Okay? If you set up if you make a membrane, then you have a permeability of the membrane itself. Whereas the flux, depending upon, although you are using the same membrane with some permeability P, then depending upon the pressure, depending upon your temperature and so on, your flux differs. So pure water permeability, pure water permeability can be determined by using the membrane. So if you have a membrane and you put it into the so-called the Amicon cell, and fill the top of your membrane with the water, and apply the pressure, and you get some water. As a function of membrane area, as a function of your time of the measurement, right? So you measure the volume at a certain period of time. So you measure the flux volume divided by the membrane area, and the time of your operation. So you measure the weight through the membrane, the water through the membrane, and you measure that. So that should be constant at one applied pressure. And this, if you increase your pressure, then the flux will increase. So this linear plot, J divided by delta P, okay, J divided by delta P is LP. Okay? So slope of the plot is called the hydrodynamic permeability because what we measured was a JV versus delta P, which is LP divided by viscosity. So if you are using the viscosity, if you are using the water, the viscosity is 1. So that's the slope of the J versus delta P is LP. So from this plot, you can easily measure the permeability of the membrane. So that's the easiest way of measuring the flux and the permeability of your membrane. So when you report the property of the membrane, you can report it to the LP rather than the flux itself, because flux depends upon the applied pressure. Unless you report you apply the same pressure, like a 10 bar or a 5 bar or whatever you report. But usually the pressure differ. Therefore, it's much more, if you're developing the membrane with a different porosity and so on, it's much more convenient to report the permeability rather than the flux. Next is about the microscopic technique. Well, we have several techniques which we will cover. If you were in the area of polymer synthesis, then I think you have to know about these characteristics as well, characterization methods as well. In the microscopic techniques, we have a scanning electron microscope, field emission scanning electron microscope, or FESM, is quite common these days. We have a transmission electron microscope, atomic force microscope, and so on. So we will look at one by one. So scanning electron microscope is the technique that you can get the image of particularly the surface of the membrane, or the cross section of the membrane, or the surface, of everything what you are talking about, because I think you have a picture here. So if you put the specimen membrane sample in the bottom, and your electron gun will bombard the electron beam, and through this anode and the scanning tunnel, your beam will be focused to the one surface of the membrane, so that you instead of the electrons go through it will be bombarded, reflected the electrons, and can be collected to the imaging analyzer. So what you do is that your electrons will be refracted. So refracted electrons due to the surface of a membrane will be scanned. So you look at the surface of your membrane. Later, you can take a look at the transmission electron microscope. Instead of scanning, we have a TEM. So TEM will transmit, electron beam will be much more stronger, so that you have a transmitting the image of the membrane. So much more smaller in the resolution size can be detected. Anyway, using this scanning electron microscope, we measure the image of the surface of the membrane that we are looking at. So usually, this is the typical example of the cross-section and surface or cross-section, the image or surface of the images as well. You can tilt this specimen so that you get nice images as well. We have along the line of the characterizing the surface, you can measure the surface of the image, membrane image, using the atomic force microscope. Atomic force microscope is the one that you expose this surface of the membrane with the laser light, and cantilever sort of a needle will be scanned through, so that you will measure the contour of each surface layers, and you get the image of those surface as well. Well, this will not be able to get the cross section, but only the surface image will be measured. Will be possible to measure. So this is the typical example of the AFM. This should be, the color, the image. The dark area is usually the lower in the valley, whereas the light area is regarded as highly, the mountain. So you have a mountain and valley type of the images, and from this scale, you can get the images. Anyway, we have the AFM. So, in AFM mode, in AFM, we can scan the surface of the membrane in the dry stages, or we can measure the surface of the membrane in the wet stages, which is a little bit very difficult because of the softness of the surface of the membrane as well. Anyway, it's quite useful, so that AFM and SEM images is, of course, will be quite used in your papers and research. Before we go into the TM, I think we can take a look at the mechanical properties. Well, mechanical properties are quite important because usually when you are dealing with the membrane might be fragile. Membrane could have a green strength, or could be put it into the module stages, and then your module might be in the static state, but your modules might be in the dynamic stages. You have to, in some cases, you have to apply the pressure or pulse, okay, through the membrane module. So your fibers or membrane should have some mechanical strength to withstand the external forces. Therefore, we need some mechanical properties. Mechanical stability and the swelling behavior of the membranes can be determined by the cross-linking density or the crystallinity of the polymers, and so first of all, the crystallinity can be detected by the X-ray, the wide-angle X-ray and the small-angle X-rays. And degree of cross-linking can be measured by many other techniques. But the simplest way of measuring the cross-linking density is by measuring the swelling behavior of the polymers. Because if the polymer is not cross-linked, then the polymer can be dissolved in organic solvents. If the polymer is cross-linked, so that you have some network structure, then polymer cannot be dissolved because of these links, okay, between the chains, between the main chains. But rather it's swollen because it absorbs the organic solvents and can be swollen in stage. So by measuring the swelling degree, we can calculate the cross-linking density. Infrared spectroscopy is also used to measure the cross-linking density as well, if you know the exact functional groups in your charges. Typical mechanical property measurement can be done by this tensile strength measurement, and what it is that you get the specimen and you pull in one direction, okay, which is the axial direction, so that you make a stress to the specimens, and of course the material or membrane will be stretched. Okay? So you plot, you get the response, strain and the stress, because this is the original stage, and also of course this curve depended upon your specimen size and the thickness of your specimens. So you have to record your thickness as well as the width of the specimens to measure the exact elongation percentages and the tensile strength. So this is the typical example of a membrane sample, and this point is regarded as a breaking point, and the strain at this point is called the strain at break or elongation at break, and this point is called the stress at break. Okay? And you see this refractive points. This point is called the yield point, and this is the yield stress and yield strength. Yield strength and the yield elongation at yield points. Now, initial slope of the stress versus the strain is called what? It's called Young's modulus, because this is like a spring constant, right? because if you look at the spring, then it will be stretched in constant rate, and this is called the spring constant, or Young's equation. Young's equation is the one that your modulus dependent upon your stress divided by the strain. And so the slope is modulus, or Young's modulus. So this is the typical example of the measurement of your membrane properties, or the mechanical properties. Bear in mind that we have various test methods depending on your materials. If you're dealing with polymer, then you have a certain specification. If you're dealing with metals, if you're dealing with ceramics, or even the fabrics, you have different specifications. And usually the ASTM, American Test Standard Method, American Standard for Testing Method, ASTM, is quite useful. Of course, each country may have those specifications, but depending on the material categories, we have ASTM B something, ASTM D something. You have different the methods. Of course, the mold is very important. So the mold, you need to maintain the nice status of your molds as well. So we have a small micro, the tensile meter in the laboratory. This is the modulus that I'm talking about. What about the mechanical strength of the mechanical characteristics of the ion exchange membranes? Well, ion exchange membrane contains some ions in the polymer backbone, so it may swell depending on your charges and pHs. So swelling stability and the dimensional stability can be determined in various solutions as well. Of course, the hydraulic dynamic permeability is very important as well, and depending on your pH. It's a little complicated than the non-ion exchange membranes. Sometimes water stage can be determined by the DSC, dynamic the differential scanning calorimetry, or IR or NMR. Let me briefly mention to you about the different state of water in using the DSC measurement. What you will do in DSC measurement is that you measure the enthalpy changes, a change in enthalpy as a function of temperature. Okay? When we are looking at the polymer, then we are at a little above 0 degrees C usually. When we have a transition curves, we can say that we have a glass transition temperature, or we may have a crystallization temperature or the melting temperature, depending on your. This might be a little reverse, but anyway, we can detect the TG and TM using DSC, of course. This is the bulk property of the polymer. But if we measure the water state in ion exchange membranes, we can scan those samples with the water at low temperature, because water is in the liquid phase above 0 degrees C, and the water will be frozen below 0 degrees C. But this freezing behavior will tell us what's going on about the state of your water in the ion exchange membrane stages. Because if you think about the ions, or this is the membrane surface containing some ions, but water may have some interaction and different interaction depending upon your charges. Now, it's known that we have three types of water. First layer is called the bound water. Which is the first layer of the water just above the membrane. Okay? And this is very tight and tightly bound with the membrane, so that the water is quite strong. The bond strength is quite strong. And we have some layer which is called the intermediate layer or intermediate water. And we may have a free water, which is a little far away from the surface of the membrane. Okay? Now, if you assume there's a three-layer structure of the water above this, the ion exchange membrane or even the membrane, then we can detect using these DSC curves. Now, if you scan this from, say, 100 degrees C, sub-zero, minus 100 degrees C, we may have some curves, transitions, like this in the water stages. If you look at this, this is, well, this amount, or if you have some portions, then this amount might be related with the bound water, because bound water will come quite at a low temperature, whereas the highest one might be related with the amount of your free water, and this might be related with the intermediate water. So by measuring the area under the curve, okay, by measuring the area under the curve of your isotherm of DSC of the membrane containing water, you can measure the free water amount, bound water amount, intermediate water amount. Okay, of course this is not an absolute value, because this is a sort of a relative value of the water content, but we can measure the free water content and bound water content depending on your charges. This technique has been known for about 40 years. This technique has developed in 1970, and so far I think, although there is a little bit of controversy about what's going on, but still it will give you some nice interpretation of your data on the water stages of your ion exchange membrane usually. Swelling. I told you that swelling is very important if you're talking about the water. So swelling is a full. Swelling of the water in the membrane is containing free water, intermediate water, and the bound water as well. So let's talk about the swelling measurement. And swelling is a very tough method. What you do is that we measure the weight of your sample, of your membrane, in the wet stage, and to measure the weight of your membrane in the dry stage. And by calculating this equation, we can measure the swelling degree based on the weight. Sometimes this W wet could be replaced by W dry. Okay? So you should be very careful how they calculate the swelling degree depending on the wet base or a dry base. Okay? Right? So the weight of your membrane in the dry state can be easily done. This I don't need to explain in detail. But what about the swelling, the wet stage? Well, usually the membrane could be put it into solution. If it's water, then you put it into water. And let's keep that stage for some time to reach an equilibrium. Okay? In other words, there is no change in the weight. For example, if it's put into water for 1 day, and after 1 day you can take it out and you just blot it, the surface water of your membrane with some Kim wipe and measure the weight. Okay? Which contains a dry weight of the membrane plus water that was contained during those one day. Okay? Now during this measurement, I told you that this is not an exact value because usually you may have a little bit of error depending on how hard you press your water. Okay, whether you dry, whether you press during the daytime, or even the rainy day, or the very clear days like today, or with low relative humidity, you may have a little bit of errors in those measurements. But anyway, this will give you a very nice value if you average out some of those measurements. Can be very stable. Anyway, you have to report standard deviation of your swelling measurement anyway. So the swelling is quite a useful property, and the state of water could be quite more scientific in your interpretation of your data. Next is about the filtration test. Okay? Now, we measure the pure water flux and the permeability, hydraulic permeability or liquid permeability. This section will give you a rejection properties, separation performance. So usually R gives you a rejection. So as you can see in this slide, we have a mixture of a larger molecule and a smaller molecule in the left-hand side or feed side, and that could be separated through the membrane, and so that the smaller size in this picture is penetrated through, whereas the larger molecule still maintained or kept in the feed side. So we have to think about how fast your small molecule comes out, like a permeability or flux, and also the separation ability or selectivity or separation factor. So I think I will tell you what's the difference between separation factor and selectivity later on. But anyway, we have to know about how the membrane discriminates or differentiate the larger or small molecules. Okay, that's called this R or rejection basis. Now this depends upon some of these radius of the molecules. So radius molecule of the large molecule and the small molecule will be used to measure this rejection of your particle, if it's particle. This is very typical in the filtration processes. Okay, filtration process. If you're using a pretty non-woven fabric as a filter, this is very typical, the measurement of your particle. But in the case of membrane rejection, we can think about the rejection as a function of the concentration of the solute in the feed component and the permeate component. So if you measure the concentration of your membrane at both sides, for example, concentration of your sodium chloride solution in the feed side and in the permeate side, okay, you can measure the rejection anyway. So rejection is very important for the reverse osmosis, nanofiltration, and so on. So we have to know about this rejection concentration. What about the molecular weight cutoff? Molecular weight cutoff is the one that when you have a larger molecule, when you have a certain pore size and have a different size of your molecules. Some small molecule, smaller than this radius of, smaller than this the pore size might be and can be penetrated through, whereas a larger molecule, larger kinetic diameter, then this the pore size cannot, right? So if you have a different size of the solutes in the feed, then we pressurize them at a certain pressure and measure how they are coming out. Is the indication of MWCO. Now, what you can see here in this graph is that this is the molecular size. So this is the molecular weight of your solute. So you have different molecular weights and pass it through in the mixture. And you have some breakthrough point here. In other words, a rejection is almost 100% here if it's a larger in size of your molecule solutes. But if it's a smaller, you don't have any separation. So everything smaller at, in this case, smaller than this size will go through. So MWCO is defined as the solute that has a rejection of around 9% of rejection. It's called MWCO. So in this case, it's about 10 to 3, which is about 1,000 or 1,500 or something like that is called the MWCO in this case. Well, this is easy to determine this MWCO because we have a very sharp breakthrough point. But in many cases, you have a little different, you have something like this curve, and it's very difficult to, whether you have to define this 90% or 60%, something like that. But anyway, MWCO is defined as at least 9% rejection point is called the MWCO. Yes, we have quite a sharp cutoff or diffuse cutoff, but MWCO could be determined anyway in this case. In some cases, particularly if you wanted to use the membrane in the biological system, you have to think about the biological test or bacterial test or contaminant test. So when the bacteria is contained in the feed, how well the membrane in terms of biological stability is maintained is the challenge of is the essence of this test. Okay? Usually they use Pseudomonas diminuta. It's more like 우리말로는 뭐 대장균이라고 하죠. Pseudomonas. So they use this certain concentration of the bacteria containing feed, and they measure the stability of the membrane later on. Okay? Next topic is about the pore size. Okay? So we have talked about the permeability, stability to the biological system. We have talked about the water stages and how the water is maintained. But we need to think about the radius of those pores, if you can measure. Well, radius of the pore can be measured by many methods. Right? We do not have any specific single universal methods, but we have several methods to measure those pores. Usually, this is the non-destructive method. In other words, we do not destroy the membrane during the test. It's called a non-destructive method. And bubble point method is the one that is called a non-destructive method, so that it could be widely used. So after test, you can still use this membrane for your application. What it is that we use a liquid. So bubble point method uses a liquid to be held in the membrane pores. To be held in the membrane pores and measure the surface tension and capillary forces. So by measuring those properties, we can measure the size of the pores. So pressure, the contact angle, surface tension, all of those will be used to calculate this radius of the pores. So bubble point method uses this type of schematic container test here, whereas we have a liquid and we have gas coming in, and you put the membrane inside of the valves or on the bottom of the valve, and by measuring the gas. So first of all, we wet the membrane with water for hydrophilic or the alcohol water mixture for the hydrophobic membranes, and then increase the pressure. Then after some time, so water will be coming out later on, of course. So by measuring the pressure, so when what kind of pressure that the liquid is coming out will be the indicator of the size of the pores. If the size of pore is large, then the water in the wet membrane will come out at low pressure, whereas if it's very small, the water will be coming out later on because of the capillary forces. We can replace this water with the mercury if the pore is very small. Okay? If the pore is quite large, that's no problem, but if the pore is quite low, quite small, then we can use this mercury instead of a liquid. Okay? So mercury porosimetry uses the non-wetting property of the mercury to gain information about the polar characteristics of solid materials. We can use this for the membrane or the inorganic membrane or metallic membrane, whatever, to look at the porosity, pore volume, and pore size distribution, and also about the density as well. So in this case, we use a dry membrane. So dry membrane is exposed to the certain volume of the liquid mercury. Mercury is quite mobile. I'm not sure whether you have dealt with mercury or not, but it's quite mobile. You cannot catch. It's difficult to put those with a spoon. But it has a good interaction with copper. Anyway, it's very shiny. It's very shiny. It's even it's like a mirror. You can make the mirror out of this mercury anyway. But you have a high surface tension, so the surface of the mercury with the chalet will come to the valley like this. It's not just a flat at the edge. And anyway, I think you can use this mercury as a liquid form. So pressure. So your dry membrane is put into the liquid mercury and apply the pressure. Then mercury molecule will slowly go into the pore, and the force that comes through, and the amount of mercury that is coming out is measured. By using this, you can measure just like a bubble point, the porosimetry. We can measure the pore size and so on. We can have a gas and liquid displacement type of the bubble point test. It's exactly the same as the bubble point meter. We can use the liquid and the gas. Instead of water, they use certain liquid, such as a pore wick with a certain tensile strength, tensile tension, surface tension, and it's exactly the same as bubble flow method. So using this, PMI method, the Porous Material Institute, we can measure this gas flow versus the pressure. So if you apply the high pressure, then gas flow will be much larger, meaning that we have a highly porous in nature in this region, whereas a small pore size could be detected in this region as well. So mean pore size is determined by the 50% of the dry floor, so that this is determined by the, this will tell us the mean flow pore size anyway in this case. We have the PMI, we have the capillary flow porosimeter by PMI, and it's quite nice to have this machine. We can have a liquid displacement method, which one liquid will be replaced by the second liquid. It's called the liquid displacement method. Depending upon the availability of the machine, I think you can have different machines. Anyway, you can replace many of the other liquids, like water and isobutanol, instead of air and mercury or air and water, which we have just talked about. Depending on the availability of the machine, you can measure the porosity and pore size distribution. So far we just talked about the pore size and measurement of pore size distributions and so on. We will talk about the characterization method of the homogeneous membranes without any pores. In this case, we have to know about the TG, glass transition temperature, because we are dealing with the polymer itself. If we have a polymer with a crystallinity, we can check with the crystallinity as well. What about the sorption and diffusion? Okay? Sorption and diffusion. If you're dealing with gas separation membrane, we need to know about how well the gas molecule will absorb to the polymeric structure or dissolve. So the sorption and dissolution, or diffusion even, is one of the methods to measure. And in this case, permeability, hydraulic permeability or gas permeability, or selectivity. I'll tell you the difference between selectivity and separation factor, but selectivity and permeability are the intrinsic property of the membrane. Right? And this is the interesting parameters, because this will tell us and exactly the same as the same parameter with reverse osmosis. The selectivity is quite common in gas separation area, whereas in the RO membrane area, the selectivity is replaced by the rejection. So they tell you about the rejection. Permeability, the terminology of permeability is the same, whether we are talking about the liquid permeability or hydraulic permeability. Hydraulic means water, so water permeability or gas permeability. And the permeability, the species of penetrant is just in front of this word. Well, before we go into this in more detail, we can talk about the contact angle measurements too. Contact angle is a rough indicator of how your surface is composed of. Now, still, the other Young's equation is the one that is telling us about the contact angles. Now, when we have a surface of the material, and if you put the water on top of the surface, the angle between the liquid and the surface is called the contact angle. If the contact angle is zero, that means that there is a very good contact, very good spreading of the liquid on the top of the surface of this material. Whereas if you have a contact angle which is much larger, then there is a low surface tension, so that the material will be flowing anyway. So there is no wetting. So wetting is determined by the energy of the work between the liquid and your surface of the material. So S or G or L in this subscript will tell you about the phase of your the liquids and so on. So if it's a hydrophobic membrane, then contact angle is pretty large. If we are talking about the filling membrane, then the contact angle will be quite low. So contact angle is although it's a little bit rough estimate of the property of the membrane, but it will give you anyway some indication of how the membrane surface will look like. We can have a superhydrophobic membrane, just like a lotus root. I'm not sure, we don't have a lotus picture here, but lotus, okay? The water is not spreading on top of the surface of the lotus root, lotus leaves, but rather it's flowing because the surface of because of the very rough surface of your membrane. Okay, so surface is not smooth, but if you have a pretty rough surface, then water cluster cannot spread out in the smooth surface, but it's the cluster is much larger than the size of this valley, so that you have a water cluster sitting on top of this the two mountains or three mountains, and rather so that the contact angle between this the water and the surface of the lotus leaf is above 150 degrees C. So we can think that that's regarded as a superhydrophobic, and the criteria is that the contact angle above 150 degree is called the superhydrophobic. On the surface of this lotus leaf, we have a pretty roughness, and they have a small hair on the surface of the membrane. So this small hair is on top of the surface as well as the rough surface will provide you for the lotus leaves to become superhydrophobic. So in many cases, they mimic this lotus-like structure of the surface, and you can make the superhydrophobic membrane as well. This is the typical example of the differential scanning calorimetry. You can measure the glass transition temperature and the melting temperature, and of course the crystallization temperature of these transition regions. And also by knowing this area under the curve, we can calculate the crystalline degree, or degree of crystallinity, if you have a standard samples. Okay? Now, later part of this characterization method is about the ion exchange membranes. In the ion exchange membrane area, we have a little bit different characteristics than what we have talked about. Because ion exchange membrane has some charges, we have to think about how many charges that we have on the surface and on the bulk. Okay? And because we are dealing with the two ions, like a negative ion and positive ion. In other words, if you're talking about the cation exchange membrane, we have a negative ion in the membrane, whereas in the feed, you may have a negatively charged ion or positively charged ion. And this is much more complicated than non-ion containing the polymer, because non-ion containing polymer has neglecting the ion effects, whereas if you have ions on the membrane, then there are very much complex interactions, because if you have a negatively charged ion on the polymer, then negatively charged ion in the solution may have the repulsion, whereas a positively charged ion in the feed will be attracted to the negatively charged sites in the membrane itself. And of course, this interaction and repulsion depended upon the type of your charges, right? And type of your solute, whether you're talking about the monovalent ion or bivalent ions, or all the charge and dissociation and effects and so on. And also, if you apply the electrical pressure, electrical charges in the system will be much more complicated as well. So there is a lot of complicated structure, and we have to think about the electrical charge of the membrane and in the solution. We have to think about the resistance to the electrical resistance in the electrolyte solution. We have to think about what's the type of the charges. Fixed charges is the terminology that is related with the membrane charges. What about the density of the charges? What about the distribution in the membrane matrices? So this all gives you a very complicated structure. We have to think about the pump selectivity of the membrane for different ions. You have to think about how fast the water will transport, particularly the water will transport through this complicated system, and the neutral systems. What about the stability issue, in terms of mechanical issue and chemical issues? We have to think about the swelling as well, water swelling or ion swelling of the electrolyte solutions. Now, I just wanted to close this talk, and I will continue on this coming Friday, because it will be one issue. If you have a membrane with the negatively charged site, which is called the cation exchange membrane, and if the counter ion is a proton, and the counter ion is sodium, it will be different. Okay, sodium containing one versus the proton containing one have a different solubility, right? In the water, or even in the alcohols, or even in the organic solvents. One form will be dissolved, and the other form will not be dissolved. So this is the situation. Although you have the same charge in the membrane, and same density, same distribution, if you just wanted to change the opposite, counter ion, you have a different solubility. So this is an issue. That's why it's very complicated, very different from the neutral ion containing polymer membrane that we have already talked about. So far, any questions or comments? I'm sorry that for those of you who may have already go through with the polymer chemistry course and the membrane characterization course, it will be much repetitive, and it's a kind of introductory session. But for those of you who have not been to polymer area or membrane area, this might be instructive. So I'm sorry about the level of your understanding, but I think we need to, this is more like a basic the study that we have to talk about. Any question, Bibi? No question. Okay, I think we have about 5 minutes, but we can continue our discussion about the ion-exchange membrane characterization this coming Friday. Okay, see you.
Thank you.